Welcome to the Nano Entrepreneurship Network podcast, in which entrepreneurs who have transitioned ideas into the marketplace share some of the lessons they have learned as they navigated the technology development pathway. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Today, I am joined by Vinayak Dravid, the Abraham Harris Professor of Materials Science and Engineering at Northwestern University. Vinayak is the founder of a company called MFNS, or Multifunctional Nanostructures for Environment, Energy, and Biomedicine. Vinayak, thank you so much for joining us today. Can you talk a little bit about how you started this company and what it's all about?
Yeah, indeed. Just a few years ago, we are starting to realize that in order to make impact, not only do we need to do science, which we all do and we enjoy, we also need to show that the science has the opportunity for translation into technology through the bridge of, we call it engineering, right? So we have nanoscience, like most of us do. Nanoengineering is needed to make it into nanotechnology. And so one of the areas we felt very strongly about at the time is the environmental pollution, whether it's oil pollution, whether it's phosphate, heavy metal. And we realized that there is a tremendous opportunity for nanotechnology to make an impact, but need to make an impact in a way that is scalable, cost-effective, and readily deployable. And these are very severe constraints imposed on any technology. And so we realized an opportunity by using sponge or membrane as the substrate material, which are flexible, very cost-effective. In most cases, they're actually discarded. And in fact, I just recently read that 500 million tons of sponges are actually thrown away and discarded every year. And if you can just take a portion of it and use it as a value-added product. So our technology is based on, as the title says, MFNS, multifunctional nanostructure. So we take nanostructure, which are multifunctional, and we produce them using green chemistry, extremely large quantities, using very simple precursor, which is iron-based, carbon-based, which is environmentally benign. And we have what you call it the story of R. So we use a reduced amount of material, which is in the form of coating. And this coating allows the pollutant to be absorbed onto the surface using just one parameter, and it can be used to release it. So in the case of oil, our OHM sponge technology absorbs only oil and not water. And the way to release it is squeezing it. Just like you squeeze our household sponge, you release water, it releases oil, and then it's ready to reuse again. So unlike single-use solvents, which are used in industry, this technology has the potential, and we have shown this in our US Navy facility, which is actually a gatekeeper for oil spill technology monitoring. And we showed that 1,000 times less waste can be created with our technology. So now in this world where we are reducing waste, we are reducing amount of material we use, we are looking at circular material economy. We're very excited that MFNS is providing a solution which is scalable, cost-effective, and it can be readily deployable with a minimal drop-in consideration. So we're very excited that this platform technology has the ability to remediate environment with parameters that are business-friendly and business-centric. And so there is an opportunity for us to show impact on environmental remediation and still make it a viable business.
So you talked about reusing sponges that now are headed for the landfill. So do you have a strategy for collecting these used sponges? Do you have a place where I should send you my kitchen sponges?
Exactly. So one beautiful thing about not just the American system, but the worldwide is there are a lot of volunteers, there are a lot of NGOs which care about environment. And so initially we wanted to have consistency. So we have a commercial source for sponges. But as you can imagine, as time goes by, we would rather use discarded ones because that way, when you get your, December present, whether it's Christmas, Hanukkah, you have a small device, maybe iPhone, but the rest of it is packaging that you typically throw away. So if there's a mechanism by which we can collect the packaging material, then our even the initial cost of the source would be even minimal. Regardless, the idea is still get the sponge, whether it's through commercial means or through volunteer collection. And all we do is dip coat it. So as simple as that. So it's a very one-step process to make it into value added. And that's where we feel is exciting because it's very cost effective, it's scalable because sponges are scalable, and it's immediately drop-in technology. Instead of sorbent, you use the same. All you do is you squeeze it if you need to. Otherwise, you can still get 20 to 30 times more absorption than the current technology. So both as a one-time use or multiple use, we think our technology has tremendous potential.
Can you talk about the role of nanotechnology in this technology?
So one of the beauty of nanotechnology is two things. Correct? It's not just about making things small, which is obviously one of them. The other is at that scale, the materials behave differently, right? And they have the gold is no longer gold at the nanoscale. You can have red gold, you have blue gold. So in the same spirit, we have two components that make up the OHM sponge or all the other technology for environmental remediation. One is a carbon in the form of graphitic carbon. And secondly, you have nanostructures in the form of metal oxide. And this is iron-based oxides. The nanostructures based on iron oxides are truly nanoscale. So they are less than 20 to 30 nanometer. Why is it important? Because they behave what is called a superparamagnetic behavior. So that means they're magnet only if you bring an external magnet. Otherwise, the magnetism goes away. So it is the best of both worlds. It is magnetic only in the presence of magnet. And that allows the motion of the sponges using external magnet. Secondly, at that length scale, the electronic structure is different than nanostructure. And what you need is affinity for pollutant by this nanostructure only for that particular pollutant. You don't want everything else sticking to the nanostructure. So by tailoring the size and the composition, you can tailor the ability of this nanostructure to sequester phosphate or oil very precisely. So in a mixture of other things, it is very selective. So this nano enables two things. One is very high surface area. For small amount of material, you can have very large accumulation of pollutant. And secondly, by changing the size, it behaves very differently. So as a result, the electronic structure at that length scale can be made adaptable or affinity for the specific pollutant. So this is certainly one of the unusual outcomes of nano in this case is not just the surface area, which is often the case for nano, but also very unusual behavior materials undertake at that length scale. And in this case, that of affinity for pollutant.
So I think I didn't ask, when was your company formed?
The conceptual stage was about 2018, but the formals we started to launch in the late 2019. We just wanted to make sure that we have resources to conduct very specific tests. Because, for example, for oil spill, there's a gatekeeper or an institution called as OMSET, Oil and Hazardous Material Testing Facility. It's operated by BC, Department of Interior, but also under Department of Navy, U.S. Coast Guard, and others are involved. There's actually a 16-agency consortium called ICOPAR, specifically addressing oil spill remediation technology. So in March of this year, actually, we conducted a formal test at that location to quote the people involved in that test. They have said they have never seen this type of technology before, and they're very excited to be part of testing that showed that the ability to absorb oil 30 times its own weight, you can reuse it 40, 30, 50 times. So you're looking at 1,000 times less waste. And they're very excited to be part of this technology. And that is where we are right now. After this test, we have given it basically a validation from a test agency. And now we are looking at specific customers and their need and how we scale up this technology.
So it's a relatively new company then. It sounds like you're in an exciting stage. Can you share maybe some advice that you've been given that you found particularly helpful as you were starting on this venture?
There is a lot of innovation and entrepreneurial spirit in America. That's how our country was founded. And there's something we take a lot of pride throughout the world. So there are two parts to high technology. Often when we say high technology, there tends to be information technology angle to it. So let's separate information technology or software-based to hard technology. So ours is what we call is a hard technology. It's physical. So I often use a joke when there's an oil spill. There's a student asks, is there an app for oil spill? There is no app. You have to physically remove it. There's no software that can do for you. So one of the critical things in hard technology is validation, ability to scale up, being cost effective, being a drop-in technology because it has been around for a long time. There's a reluctance for change. So we want to show value with minimal perturbation to the supply chain. So my best advice is always to work with partners who understand the bigger problem. So you might be looking at it from a narrow angle because you're excited about your technology, but how is it going to get deployed? What are the issues and challenges when we deploy it? Is something we don't always pay attention to. So I think my advice to those budding entrepreneur is to look at the big picture, not just get bogged down with your narrow perspective, because that big picture will tell you both whether there's a need for you to pivot perhaps, or need to expand your product line, or you need to be focused. And one of our challenges is exactly that, because we have the technology we feel can be addressing many different pollutants, but we need to demonstrate at least one or two in a cost-effective manner. So my other advice is both to explore the big picture, but also have focus so that you can demonstrate the utility, efficacy, cost effectiveness, whatever is the consideration for that industry, so that you can show that effectively before you jump on to other complex problems.
So you have a couple things in there that I want to follow up on. The first thing is you talked about the need to do validation, and you described some of the tests that you've done recently. One of the other things that we often hear from small companies and people getting started is the need for characterization and equipment. As you mentioned, this is a hard technology, it's physical. So how do you access the instrumentation resources you need to take measurements and do characterization?
Excellent question. So I often say it's a nanoscale origin of a gigacell problem, right? So in order to, even if it is oil spill or phosphate remediation or any environmental challenge, the genesis of it often lies at the molecular scale, right? So you can have a model system where you can understand the concept as to why and how it happened. And that requires, as you said, a lot of capabilities, instrumentation methods, techniques. And that is what has happened in the US higher education and research intensive institution in the last couple of decades. Is they all have recognized the need for infrastructure. And this infrastructure is instrumentation, methods, equipment, because the problems have become molecular and atomic scale, right? So you want the ability to see, as Richard Feynman says, that if I can't see, I don't understand. So how do you see that interface between soft and hard at the nanoscale? That requires a lot of capabilities, instrumentation. So I'm fortunate that I run a Nuance Center, which is a facility infrastructure program at Northwestern, which is part of a bigger NSF-wide infrastructure program called NNCI, National Nanotechnology Coordinated Infrastructure. So I can sort of tell you about that infrastructure as basically a microcosm of my own company issues. Because whether it's large company, small company, they always have need to understand molecular and nanoscale structures, phenomena. They might have deep pockets, but they don't always have expertise. So I often say it's not just Ferrari that you need, but you need Schumachers to run the Ferrari. So you need expertise, you need instrumentation, and that is where university infrastructure is great at. In the past, we used to produce students and papers, but now we provide infrastructure, prototyping. And that's a very critical issue, because unless you get through that threshold, the football analogy is you want, first and goal at the goal line, right? But in most cases, we start many, many yards before, and so you need the ability to move the ball further. And infrastructure program like NNCI facilities, they provide that critical needs, both in terms of instrumentation, but also expertise. And even large companies at Nuance, which is a part of Shine Resource at Northwestern, you have large companies and small companies. They come because they need both ability of instruments and capabilities, but also expertise. And so that's the third leg of university, which is underappreciated, is instrumentation and infrastructure that feeds into not only internal research program and education, but it also feeds into startup culture, it feeds into SMEs, and even large companies actually are very supportive because they might have enough money to buy an instrument, but how do you create that expertise alive? And now with technology changing so quickly, they would rather work with universities in the short run. And when the need becomes pervasive, and we encourage them, instead of logging down us every day, you should buy your own equipment after you validate and prove it. And that model of NNCI and this infrastructure model has been, I think, extremely successful. And I would strongly advocate, because that becomes like a regional federalist system. So regionally, within few hundred miles of Chicago, we serve that community. We have similar such nodal sites, 615 other sites in the US. So I think instrumentation infrastructure, I think, is a critical component of any innovation paradigm moving forward. Particularly now you're designing material. It's not just physical materials, synthetic biology, molecular biology. We are now building blocks are now atoms and molecules. So ability to position them, manipulate them, fabricate them, characterize them is now become an integral part of any innovation ecosystem. And that's what makes the university infrastructure, I think, very critical piece. So in the past, we used to be, local, but now it's become global. In the past, you used to have or claim for big groups, but now it's about network. And so the paradigm is shifting more towards interconnected quilt type of approach. And each one is connected to the other. And you try to remove one, and you'll see the whole quilt is moving. And that is the ecosystem I think we have created in the US, and we need to nurture it and make it even better.
I love your description of the user facilities in the ecosystem that you're now a part of as an entrepreneur, as well as your experience as a professor. Can you share any insights you had from other small companies or people that have started businesses in your ecosystem that you found some synergies with?
Yeah, there are a lot. In fact, what we learn from in different technologies, we interact with some companies where they have extremely high value products such as MOF, the MOP, metal oxide framework structures, for example, also called covalent organic framework structures. So materials which are specialized materials and they do certain functions such as pollutant or poisons, sequestration. But we realized that ability to scale up, creating cost effectiveness, using materials which are like water based. So there are certain things that we learn from these interactions. And what is the root cause of the problem? So ability to ask questions at the molecular scale, nanoscale, and to see that implication of what we do at the nanometer scale has implication at the macro scale is really very gratifying. One best analogy is the human genome, right? The Human Genome Project was about sequencing DNA. And this nanometer scale object, DNA, carries so much information and how we may behave or what disease we might be prone to. So there's this sort of a form function relationship that is established paradigm. And now there are similar such paradigms and the establishment of form structure that we see in many other arenas. And so as a result, we feel that this interdisciplinary approach to problem, bringing in expertise from different angles and using instrumentation methodology as a way to go deep dive into that particular surface, fluid surface interaction, it's more philosophical. I believe that's where I come from typically. And it's not one single thing that is a silver bullet here. Is this creating that ecosystem from science, technology, but also creating education and workforce development. So we do a lot of open houses. We do a lot of visitors from inner city youth, and especially on weekends even. We used to have when Rahm Emanuel was the mayor, and now we do it with Lori Lightfoot in Chicago. The idea is to inspire young colleagues and the emerging generation that you have the wherewithal to address some of the biggest problems in the world, whether it's energy, environment, and through this education and outreach. So all three aspects of what we do, research, education, workforce development, and outreach, all are connected to facilities, and nanotechnology provided us with this singular rallying cry to bring things together. And for that, we are thankful for NNCO.
Well, I want to thank you for taking the time to talk with us today. This was a lot of fun. I have a final question for you, and that is, what would be your advice to a faculty member that was interested in starting a company?
It's a great question. I mean, there are so many answers to it, but I'll try to make it short. So one is, I think, being, as I mentioned, be aspirational, ambitious, ask questions which are deep questions so that you get the full context. So that's a more generic advice or approach. The other is when it comes to any technology, I think cost effectiveness, deployment, scalability are very critical consideration, particularly in hard tech. Correct. In software, as you know, there are different ways, a completely different business model. But I often say you're not going to build a bridge with an app or build a space product with DNA, right? So you need hard tech, and the hard tech considerations are very diverse and extremely rigorous. And so it's very important to have focus and also look at cost effectiveness, scalability, and how effective it would be in a deployed condition. I think those are important considerations that allows you to then focus on development of the business aspect of the science that we love. But going from science to technology is a very tough bridge, which is the engineering bridge that you need to cross very carefully. I think that's my best advice.